Bienvenidos, Ushamdid, and welcome University of Maryland Global Campus learners from the CMIT-456 Section 6380 course for the fall 2021 semester. This is the CCNP ENARSI course, or the Enterprise Advanced Routing and Services version 8 course curriculum from the Cisco Networking Academy. And in this activity, we're going to be taking a look at Packet Tracer 6.2.1, where we're going to be implementing multi-area OSPF. And more importantly, we have a number of questions that we're going to be addressing at the end of the activity. And they're questions that typically come up from learners when they first are exposed to multi-area OSPF, and specifically the behavior of the area border routers, or the ABRs. And in this case, router 1 and router 3 are our ABRs. All right, so let's go ahead and dive in here, and you can see we've got the addressing table over here to the right. And we've got some instructions that are pretty straightforward, and we're going to start out here on router number 1. As you can see, router 1 is already up and ready to go. So we'll go from user exec to privilege exec with the enable command. And then we're going to get into global config. Now, the first thing I'm going to do is I'm going to say do show run and pipe that to section router OSPF. And what I'm looking for is checking to see if there's already an OSPFv2 configuration on router 1. Now, as you can see here, there's not. So from here, I'm going to say router OSPF, and they've asked us to use process ID 1. Now, remember, the process ID is a locally significant value. In other words, I could say router OSPF 1 on router 1, router OSPF2 on router 2, and router OSPF3 on router 3 using 3 different process IDs, and the neighbor adjacencies between 1 and 2 and 2 and 3 will come up, and everything is going to work just fine. Now, would you do something like that? Is that a good idea? Probably not, right? Usually what you're going to do is you're going to decide on what the process ID is going to be, and you're going to go ahead and go with that. Now, since this is the Advanced Enterprise Routing course and MPLS is part of the discussion, note that in this context, what I just said is true. The process ID of the OSPF router process is locally significant. In an MPLS Layer 3 VPN scenario, that is no longer a true statement. The process ID does play a role in whether you're going to see inter area type 3 LSAs, or if you're going to see type 5 external type 5 LSAs. So make sure that you're aware of that when you start to transition into that MPLS world, that the process ID does make a difference. And so let's go ahead and we'll say router OSPF 1. And the first thing we're going to do right out of the gate is we're going to set our router ID to quad 1s. Now remember, that has the format and appearance of an IP address. However, it's not an IP address, right? Now there may be a loopback address with that IP on it, but this router ID value is not an IP. It just has the same format as an IP address. And so we set the router ID to 1111. And it wants us to advertise each directly connected network into OSPF on router 1. So directly connected networks, let's go ahead and say do show IP interface brief. And you can see we've got our interface assignments here. And I'm just rereading this. Configure each network in OSPF, assigning areas according to the addressing table. So the addressing table shows the areas. Now the question is, because we've got multiple ways that we can do this, there's really 3 different ways that we can enable the OSPF process on these router interfaces. I could go under the interface and say IP OSPF 1 area, whatever the area is going to be, area 1, area 2, area 0. Or, since I'm under the configuration stanza in the global config for OSPF, I could use the network statement. But with that network statement, there's 2 different ways I can do that. I can use the exact IP address on the interface with quad zeros as the wildcard mask, or I could use the network ID along with the wildcard mask that is the inverse of the subnet mask. And so we'll have to look at the completion percentage to see how it is that Packet Tracer wants us to attack this. Now, my guess, because they love to quiz you on whether you know the wildcard mask value for the given subnet mask, is that that's what we're going to be doing. We're going to be using network statements, and we're going to be setting things up that way. So I'm going to leave the addressing table up there. We're also going to add in some other bells and whistles. So I'm going to say passive interface default, and then I'm going to say no passive interface gig 00, gig 01, and then serial 000. And again, there's multiple ways that I could have approached that. I just decided to do passive interface default and then no passive, the interfaces over which OSPF adjacencies will be forming. Because when you passive an interface, it does not send via multicast the OSPF hello packets, right? And that's what's used for neighbor discovery, neighbor acquisition, and then neighbor maintenance with the adjacency to keep that adjacency up. So we're just going to throw that in there, right? Good practice to drop that in. And now let's go ahead and we're working on router 1 here. Let's say 10.1.1.0, and this is a /24. And so the inverse of the subnet mask of 255.255.255.0, the inverse of that is our wildcard mask, which is 000.255, right? The opposite of what you've got there. Oh, sorry. And then we're going to do area 1 because router 1, again, is an area border router. We're participating in area 1, which is out gig 00. It's also out gig 01. And so we're going to say 10.1.2.0, that's also area 0, and you can see area 1, and you can see we've got that statement in there. And then let's go ahead, and there are the two routers out here in this, this sort of ubiquitous cloud that we have out here. So we know, and I'm actually going to write this down because we'll need to talk about this later, that in area 1, we've got router 5, and we've got router 9. So router 5 and router 9, we would consider those to be sort of internal to area 1 because we don't believe we're receiving any other routing information. And we're going to check all of that here in just a second. So let's go ahead and finish this up with our network statement on the 192.168.10.0, and then the inverse of the 255, I was saying 255 and then typing 255, and the inverse of that 252 statement, which is going to be area 0, is the inverse of the subnet mask would be 0003. And so basically to get that inverse, you're just subtracting whatever the subnet mask value is from all 255s. And so if right above this you add all 255s, you'd get 0003. And that's how we come up with that value. Now, nothing's going to work here on router 2. We're going to have to configure router 2, but we're done right now with router 1. So what are some of the commands that we can use? And let's save the configuration here. What are some of the commands that we can use? Now, they provide us, if we were to scroll down just a skosh, they provide us with some of these commands, right? So let's go ahead and walk through some of these. Show IP protocols. And here you can see we've got the OSPF process ID number 1 process running. Number of areas in this router is 2, right? We've got area 0, and we're also participating in area 1. Here are the interfaces and the associated areas, and you can see the passive interfaces, right? VLAN 1, gig 02, serial 001, and we've got routing information sources, right? So the router ID value, that's what this gateway value is. So we see the router ID value, we see the administrative distance, and we see the last time that we received an update. And again, the default administrative distance for OSPF is 110, and it is very rare that you're going to change the administrative distance value. So we're going to say show IP route. We don't have any routing information here. I could say show IP route OSPF to narrow it down if you've got a lot of routing information. And let's say show IP OSPF database, right? So this is sort of the big command when it comes to OSPF. And let's take a look at what we've got here. So again, OSPF, router ID, and think of that router ID as the fingerprint or the social security number that uniquely identifies that router among all the other routers in a given area, right? And we're going to talk about the fact that area 0 up here, right, like router 2 in area 0, does not know about all of the link state information for routers 5 and 9 over here in area 1, because this is the distance vector behavior. Remember, OSPF is a link state routing protocol. It's classified as a link state routing protocol, and that classification is based on the algorithm that's used to build the shortest path tree, and that's Dijkstra's shortest path first algorithm. That is what dictates whether the protocol is classified as link state or distance vector, right? And you say Bellman-Ford for like a RIP. And so those are very different ways to communicate information in routing protocols. And OSPF is a link state routing protocol. However, OSPF, when you're dealing with multi-area OSPF, behaves like a distance vector routing protocol. And what I mean by that, and you're going to see this, is that the ABR right here is hiding the details of what's actually going on over here in area 1. And in fact, it's going to send a type 3 summary LSA into area 0. And this is the next point of confusion for learners, is when I say summary LSA, it is not a summarization of the networks that exist over here. It's not summarizing it like, oh, if I've got 2/24s here, we could get a /23. I can summarize to a 23. That is not what we're talking about. The summary and the summarization in this context, in the type 3 LSA, is stating that it's going to give you just the networks that are over here. That's what you're going to get. And so that's what that type 3 summary LSA is going to give you. It's going to say, well, here's each of the networks. And that's really all you need to know. And that's really what the ABR is doing when it communicates with area 0 here, right? It's going to send in type 3 LSAs that say that this is going to be the originating router. And hey, if you need to get to the networks that are behind me, just come to me, I'll get you there. And so that distance vector routing behavior is referred to as routing by rumor, because router 2 has no visibility into the link state database over here for router 5 and router 9, or for anything else that might be over here in area 1. It has to trust that what router 1 is telling it is true. So here are the router link states for area 0. Now the link ID, that is your router ID. And what you're seeing here, router link states, this is your type 1 LSA. It shows you the router ID for the router in question, and the advertising router gives you the router ID again. And so for area 0, the ABR router 1 only knows one type 1 LSA. It only knows about one router LSA because it's the only router here in area 0 that's actually got OSPF configured. So that's to be expected. And so now we move to the next LSA. And remember, I talked about that summary net link state, right? So into area 0, these are the type 3 LSAs that are being advertised into area 0. And as I said, it's a summary. It's like, hey, here's one network segment that's over here behind router 1 in this other area. Here's this other network segment that's behind router 1, because look at the advertising router. So The type 3 LSA that gets injected into the backbone area basically says, if you're trying to get to that network or you're trying to get to that network, just come to me, the router with the router ID 1111. And that's why the router ID value is so important, because in a link state database and in the graph, right, the shortest path first tree, it's a graph that's being built. This is how the nodes on the graph are identified. And so the type 3 LSA gets shot in here so that everybody knows, hey, if you're trying to get to any of these networks here that we've got a type 3 LSA for, just get the traffic to 1111. That's all you need to do, because then router 1, who is the 1111, will get that traffic to where it's supposed to go, because it's advertising, hey, I know about these networks over here, so just come to me. All right, and we'll talk more about the type 3s here in a second. In fact, you can see some additional information. If I say show IP OSPF database summary, right, because remember, router 1 is in it's got links in 2 areas. By definition, it is a area border. It's bordering 2 areas. But if we dig down here a little bit and we take a look at the summary LSA, here's where, and this is the actual LSA and the information of the LSA, right? Take a look here. So 10110, the network mask is a /24. There's the advertising router. So that's all the information that anybody out here in area 0 would need to know in order to get to the networks over here behind router 1. And so you can drill down and look at just the summary LSAs instead of the entire link state database. So those are our type 3 summary LSAs. So now, because router 1, again, is in 2 areas or has links in 2 areas, we come down and we're going to take a look at what link state database does it have for area 1. Well, take a look. There are 3 router IDs here, right? Because it's getting a type 1 LSA for router 9, router 5, and then its own router 1. And router 9 and router 5 also get the same type 1 LSAs. And these are the LSAs that describe the links that are associated with these routers, right? And how would we see that? Well, we could say, show IP OSPF database, and you can say router. That's going to show me the type 1 LSA. And so let's scoot down here and take a look. So you can see if we were to take a look at showed 2 links, well, here are the 2 links it's describing, right? This is the link. It shows the DR. So there's your there's your designated router address. And we're going to see the type 2 LSA here in a second in the database. And then the router interface address, right? So we can see that that is the IP for the designated router because that's the information in the type 2 LSA. It's describing who the designated router is. In other words, who does everybody need to become adjacent with, right? In order to allow OSPF to scale in broadcast multi-access network segments. All right, and so we see the 2 links that are described there. And again, if we were to go back and say show IP OSPF database, right, after looking at Area 1's type 1 LSAs, we can look at Area 1's type 2 LSAs. And that's what this net link state, Area 1. And here you have it, right? The link ID, that is the IP address of the designated router on that link. Remember, on Ethernet, broadcast, multi-access network types, there will be a DR-BDR election, right? Even if there's only 2 routers, you're going to have a DR-BDR election that's going to take place, and this is the IP of the DR. And we know that that's router 9 because you've got the router ID for router 9 right there. So router 1 on this link here, right, the 10.1.1 and 2, on this link, router 9 is our DR, router 1's the BDR, and then on this segment, this network segment, you have another DR-BDR election. Remember that. It's a per segment activity, and you can see that reflected right here. And so on the 10.1.1.2, it's router 5 that is the DR. And then router 1, we get down here, And you can see that we ran OSPF on that interface and placed it in area 0. So into area 1, we're going to have injected into area 1 by the ABR router 1 a type 3 LSA. And the type 3 is a summary. And all it's saying is, hey, here's this network, right? I'm summarizing for you what I know about right now in area 0, which is this network right here, the /30. Who's the advertising router? Well, it's router 1. So that type 3 LSA, when injected here into area 1, routers 5 and 9, if they're trying to get to the 192.168.10/30, they know, hey, we just need to get the traffic to router 1. And we've built a map of the entire area. And so we know the links that we need to take to get there. And it's Dijkstra's shortest path first algorithm that is going to get us there in the fastest or quickest fashion. Okay. So that's the database. And again, we looked at a lot more than what they're showing you here because, again, it's important to go over that. So let's finish the configuration here. Let's come on to router number 2, and we're going to move a little bit quicker here. We're going to say router OSPF1. And let me say do show run. I always like to look. Always paranoid that they may be setting us up for failure here. So we're good. We've got log adjacency changes. Let's go ahead and say passive interface default. And we'll sort out here. We're going to say no passive interface gig 00. I'm referencing the addressing table for these statements. Serial 000 and serial 001. And then, most importantly, we want to get those points for the router ID, which is 2222. And they've got to be looking for network statements here. So it's going to be 10.2.1.0. And there's our wildcard mask, the inverse of the dotted decimal subnet mask. And this is in area 0. Now, we're going to talk about which routers are backbone routers, right? Router 2 is a backbone router because all of its interfaces are in the backbone, area 0. And that's sort of the way that you describe area 0 is it's the backbone area because all traffic has to go through the backbone area. All, I should say, let me rephrase that. All inter-area traffic has to go through the backbone area. And the entire premise, the reason the backbone area exists is to provide loop prevention. Because of all traffic, it's like, think of it as like hub and spoke, right? Because when you're doing multi-area OSPF, not only is the behavior distance vector like in terms of routing by rumor and having to trust what the ABRs are telling you with those type 3 summary LSAs, you also have the component that, and I'm sorry, I just lost my train of thought right there. I'll have to come back to that. I literally just lost my train of thought I was thinking about something else. So, but anyway, you've got that distance vector type behavior there, and router 2 only has interfaces in area 0. So let's get these other network statements in here. 192.168.10.0.000.3, and that's going to be area 0 as well. And then we're going to go network, and you can see the adjacencies are now coming up. So what we can assume here is on the first one, right, that's router 4. So hanging off of router number 2 is router number 4. And all we know about router number 4 is that it also only has interfaces in area 0. So we would also say that that is a backbone router. All right, so let's get our last network. Let's get our last network statement in here, which is going to be 192.168.10.4. Now remember, in the addressing table, they're showing you the IP address, not the network ID. So if the first 192.168.10 has .1 and .2, which it does, that would be the two usable IPs, the broadcast being .3, and then here it would have to be .4 in area 0. That is not going to prompt an adjacency to come up because we don't have anything configured on router 3, although we will here shortly. So let's save our config here. And let's say show IP OSPF database, because now we've got some interesting things to look at, right? So you can clearly see that all of the link state information and the link state database is all based on a single area, area 0, the backbone area. So this would be not only you could refer to it, I guess, as an internal router, but it is a backbone router because it does not have any connections to any other areas, right? And so all the information we get, let's say, what router IDs do I know about? Well, this is important. The type 1 LSAs and the type 2 LSAs are not advertised between areas. Because you'll notice router 2, where's my type 1 LSA for router number 9 and router number 5 down in area 1? Yeah, this is how OSPF segments the areas off from each other, right? And remember, I kind of refer to that hub and spoke topology that OSPF enforces in multi-area scenarios in order to prevent loops, right? That all traffic has to come through the backbone area. And as a result, type 1s and type 2s are not flooded between areas. So router 2, who only knows about area 0, will only see those routers that are in area 0. Router 4, router 1 has an interface in area 0. Remember, router 4 is out here in the cloud. And then it sees its own LSA. And from this, it builds that link state database. Now let's take a look at network link states, right? Remember, this is our type 2 LSA. We get the IP address of the designated router, and we get the advertising, or we get the router ID for the designated router, which is router 4. And in fact, on router 1, I probably should have said show IP OSPF neighbor, because you can see here with router 4 on that broadcast Ethernet multi-access segment type, we have a DR-BDR election. Now, on a serial interface, which is point-to-point, OSPF is smart, a point-to-point network type. OSPF is smart enough to know, well, if it's a serial interface, it's a point-to-point interface, it's a point-to-point network type. We don't have to have a DR-BDR election because how many nodes can I have on either end of those points? 1, 2. That's it. You can only have one node on each end. So there is no need for the DR-BDR, because the DR-BDR, the premise behind that and the reason it exists and why Moy basically borrowed it from IS to IS is to allow OSPF to scale in broadcast multi-access network types. In fact, we could say the following: show IP OSPF interface, and you'll see right here, network type, broadcast, and then we get this. Who am I? I'm the BDR, and here's the designated router ID, right? The backup designated router ID is router 2. I'm sorry, let me rephrase that. The designated router ID is router 4's router ID, and there's the interface address. That's how you get to the designated router, and then we get the same information here for the BDR. But again, if you only have 2 nodes connected back-to-back over gig interfaces, do we need a DR-BDR? And the answer is no, you don't. So the optimal way to do that is to go under the interface. And again, I'm not going to hit enter here, but I would go, interface gigabit Ethernet 00 would be to go under the interface and say IP OSPF network, point-to-point, and then hit enter. The problem is that you have to do it on both sides, right? And we can't get into router 4 in the cloud. We're not allowed to access it. But in scenarios where you want to change the network type to point, because it's back-to-back connected with Ethernet cables, that is how you would do it. All right. So we looked at the OSPF interface and the neighbors. So those commands kind of came in handy there toward the end. And then let's slide down a little bit more here. And now let's come all the way over here to router 3, right? Because now we're going to get some interesting information going over here. We'll get into global config. And let's say do show run, pipe it to, section router OSPF. All right, so router OSPF1 passive interface default. And to pick off the no passive interface, we're going to say no passive interface gig 00, no passive interface gig 01, and no passive interface serial 00. And you can get the extra zeros for free there. It's going to take that command even though I had extra 0 in there. Then we'll set the router ID to the pre-ascribed value. And another thing that you could do here is auto cost reference bandwidth is to change the auto cost reference band. This just dawned on me as I'm thinking, did I forget a command or what did I do here? And the reason you would want to do this is to accurately reflect the metric values by setting the auto cost reference bandwidth in megabits per second to the fastest link speed in the environment. Now, you need to do this on all routers in an area, and since we can't access the routers that hang off area 0, area 1, and area 2, right? Routers 5 and 9, router 4, and I think here it's probably going to be 7 and 8, then we're just going to leave that out. But that's something else that you would want to go ahead and set up. So let's go ahead and get our network statements in here. So it's going to be 192.168.2.0.000.255, and that is going to be area 2. And then it's going to be .1, and that's also in area 2. And now the transit segment between routers 2 and 3, we're going to say network, and you can see the adjacency. And actually over here behind router 3, I thought it would be 7 and 8. It looks like it's going to be router 6. Okay, router 6 and router 7. All right, router 6 and router 7. Just writing these down because we're going to need those values here in a second. All right, and so where did I leave off here? The network, the transit segment network. So 192.168.10. So it's not going to be .6. That's the IP. And if it was 5, so it's 4 there, and you can see it. They actually give it to you there, and I just realized that they give it to you there. I was looking at the addressing table, not at the network diagram, 0003, and this is area 0, right? So now we've got some interesting information. So the LSAs are being flooded around the network. You can see that we're at 100%, but we've got some questions to deal with over here that we need to talk about because these are very important questions. All right, so on router 3, if I say show IP route OSPF, you can see that I see those networks in area 1, and I see them as OIAs, right? Type 3 LSAs, because they were flooded into area 0 by router 1. And if they're flooded here into area 0, they're going to come to router 2. It's going to send them to router 4. It's going to send them down here to router 3, right? And that's how 3 knows about these two network segments, because again, these are the only networks that are being advertised by virtue of the fact that the OSPF process is running on those interfaces. Now, admittedly, these are transit network segments, and typically you know if you've got loopback addresses on your routers, you're not trying to get to the transit network segment. You're trying to get either to the router or something behind the router. And so sometimes you might want to get rid of all of the transit segments. And you can see here, and I actually should kind of be highlighting everything here. Those are all transit segments, right? There is no OSPF destination network that's not a transit segment here, right? And so we can get rid of that information if we wanted to. And I'm going to save that for just a second because we're going to answer these questions. So which routers are internal routers, right? Now, backbone routers can also be internal routers. And because by definition, an internal router is a router that has all of its interfaces in a single area. So who are my internal routers? Well, over, and I'll just write them out here. So we've got router 5 and router 9 over in area 1 because all of their interfaces, as far as we know, are in area 1. And then in area 0, you've got router 2 and router 4 because all of their interfaces are in a single area. And then we've got, router 6 and router 7, right? And again, based on the definition of an internal router having all of its interfaces in a single area, those would be your internal routers. So which routers are backbone routers? And these are routers with all of their interfaces in the backbone area, area 0. And it would be router 2 and router 4. Remember, 1 and 3, those are the area border routers. And so we've got router 1 and 3 because they sit on the border here of these different areas, right? Area 2 connected to area 0 and area 1 connected to area 0. Which routers are autonomous system routers? So this is an interesting one here because I think down here it says autonomous system boundary router. Up here, it just says autonomous system routers, right? It doesn't say autonomous system boundary routers. It says, why would there usually be an ASBR in this type of network? And up here, it's asking you which routers are, and I'm interpreting this to mean that they mean autonomous system boundary, or you can say border, right? Both are acceptable. And that's my interpretation here. Although, why would they not just say ASBR? So if they're talking about autonomous system routers, right, the routers in the OSPF domain, let's say that that's what they're looking for, well, then that's all routers. That's every router that we've got. It's router 1, 5, 9, 2, 4, 6, 7, and 3. Because they all make up the OSPF routing domain, right? And if they're looking for autonomous system boundary routers, there are none. Because an area border router is not an autonomous system boundary router, right? And typically what you would see, and this is kind of what they're referring to, is let's say router 2 connects out here to our ISP. Now that changes things because now we got type 5 LSA information, right? We've got external routing information that's going to be coming into the routing domain. It's external to the OSPF domain. And so that would make, if it's got this external connection, now it's an ASBR. It's an autonomous system boundary router or border router. I think that's what they're asking here, right? So which routers are generating type 1 LSAs? Well, this is an easy one. All of them. Everybody generates type 1 LSAs. That is how the router identifies itself and its associated links to other routers in an OSPF area. So which routers are generating type 2 LSAs? Our DR is generating the type 2 LSA, right? And so who are the DRs? Well, it just happens that it was 5 and 9 down in area 1. And then it was 4 in area 0. And then it was always, and we didn't actually look, but it's got to be 6 and 7. Because the DR-BDR election, when the priority values are the same, right, it's going to be looking at that router ID value and looking for the higher of the two values. So which routers are generating our type 3 LSAs? Well, it's going to be the ABR, right? So that's going to generate a type 3 or multiple type 3s, depending on how much network information it's injecting or flooding into the backbone area. So router 1 and router 3 are doing the type 3 LSAs. Which routers are generating the type 4s and 5s? And again, this is an interesting question because it's related. 4 is related to 8 is related to 10, right? And so which routers are generating type 4s and 5s? Well, nobody, because we don't have an autonomous system boundary router. We would need an ASBR, and it would be that ASBR that would generate the type 4s and the 5s. And the 4 is basically, think of it like a signpost on the road. The 4 is basically telling everybody, hey, if you're looking for the ASBR, this is where to go, right? And the type 5 actually gives you the network information, right? The networks that are reachable, that are external to your OSPF domain. So how many inter-area routes does each router have? And wow, that's a good question. So we're definitely going to have to come back over here. So each router, it's talking about router 1, router 2, and router 3. So inter-area routes, let's take a look here. Show IP route OSPF. So inner area, which is your OIA, and we could see if I were to say show IP route, you would see the legend up here at the top, or the secret decoder ring. That would show you that an IA stands for inter area. Remember, intra area is just the O. It's in the same area, and you don't put an IA, right? Because that would make it confusing. But the inter area, those need to be called out. So router 1 has 2. Router 2 should probably have, what is it, 4? Show IP route. 1, 2, 3. Yeah, router 2 has 4. And router 3 should have 4 or 2. Whoops, show IP route. Just 2. Yep, just 2. And there you go. There are the OIAs. And again, those are just the network segments over behind router, the transit segments behind router 1. So how many inter-area routes does each router have? So we can say router 1 has 2, router 2 has 4, and router 3 has 2. All right. Why would there usually be an ASBR in this type of network? And the reason that you would typically have an ASBR is you would have a router, and it doesn't have to be router 2. You could have another router sitting out over here somewhere. But the reason that you would have that is for external connectivity, right? And don't be fooled. It doesn't have to be, I'm going to erase what we've got here. It doesn't have to be off router 2. It could be off of that router right there. And that, boy, that is not a good looking lightning bolt. So let's do this one more time, right? And here we are connected to the ISP. This may be where the ISP connection comes in, right? Somewhere out here in area 2. And then we've got additional concerns that we would have to talk about in terms of what type of network this is, a stub, totally stub, NSSA, you know, whatever the case may be. But that is possible as well. And the same thing is true, right? And you can have this over here, and that may go out to an ISP, right? In fact, you can have all of these connected to ISPs, right? And then you'd have in different areas, you'd have the different autonomous system boundary routers. And I was just about to do autonomous system boundary router. This is just the ISP, right? So there's all kinds of different ways to do things. But in a network like this, typically you would have an ASBR because you'd want external connectivity. All right, well, that is going to do it for Packet Tracer Activity 6.2.1, where we implemented Multiarea OSPFv2. Let me know if you've got any questions. Thank you for watching, and as always, I hope to see you in the next video.